I'll put the total mass back or take it away depending on what I'm after. Okay? Now, you've already noticed I've used the engineer symbol for the VCOM. Okay, I think we're ready here to look at this. This VCOM is equal to the value of VCOM, which is 50 here. This is a vector, see it's fat. This is just a scalar, the 50, okay? Dot U, okay? If I multiply these two together, then I get VCOM here and VCOM here. So already we've got an equation that's going to become energy conservation if we manipulate it a little bit. But we already see we have a conservation law. We have this quadratic form, and that's what we do in chapter 11 and then chapter 12 to develop the geometry of Lagrangians and Hamiltonians. The quadratic form of velocities, a vector here, A dot a matrix dot a vector B, okay, is really important for all physics. This would be a transition matrix element in quantum mechanics. Okay, or if these were equal, expectation value, you see. So, I'm making a big fuss here about something that is pretty fundamental to mathematics, but also should be in our physics from the very beginning. So that's the deal. That's the thing that's going to give us a theorem for energy, not just an axiom. Okay? But we do need this. We do need to have the VCOM be half the sum of these two vectors, half the vector sum. We do need that.
So this is for dealing with elastic relation.
This is the elastic kabong. Okay? This guy up here. Okay? So, talking about this guy, kabong. The one that satisfies time reversal, symmetry. Looks the same going forwards and backwards. Okay? So, with that axiom, I can go ahead, and I also should notice that this mass matrix is trivially transpose symmetric. Those are zero. But this is going to be the thing we'll need in general, because we're going to be working with inertial tensors of various kinds that have components all over off the diagonal. But we are going to very much like them to be symmetric for reasons that you're going to see here. So here's the deal. VCOM dot M dot VCOM is equal to, and I'm just sticking in the VCOM's T-symmetry axiom right here. Okay? So this thing became that thing. And that's for the initial vector being over here, and then I'd like to do it when the final vector is over there as well. Okay? Almost there. It's like 3-4 lines. I think it could be streamlined more than this, but I thought you ought to see all the things that come along the way. And one of them is transpose symmetry. This self-conjugate matrix is really important. I need to have that Vfin dot M dot Vn is equal to the flipped Vn dot M dot Vfin. And I will get that if the matrix is symmetric, even if it's not zero here. But as long as these two numbers are equal, we're good to go.
This looks like condition for permitticity we use in quantum mechanics.
And there it's very similar. Very similar. Very similar to having that demand for your Hamiltonian. You get that in quantum mechanics by demanding time reversal. That the time evolution operator look the same going forward to backwards. So it's very closely related. Because, you know, we're talking about flow here, and we want it to, you know, flow this way as well as it flows that way. So that's where we stand when we take that And then it's one step of just subtracting that the actual complete derivation of this thing is seen by subtracting this thing right here. Or it's flipped from either one of these equations. And then you have 1/2 mv squared basically, initially, is equal to 1/2 m final v squared. Now it's a sum over SUV and VW, mv squareds. It's this sum is a constant. And that constant is there, we actually have a value for it, which is very useful. And we have a plot for it too. There it is, very precisely drawn. Okay. Now let's see, we started at 4 o'clock, it's now 5:20. Do the arithmetic for me. How far are we?
We started about 12 minutes.
Pardon?
12 minutes even after
Okay,
the
so
4 point.
I'd like to, if you guys can stand be here just a little bit longer, we'll go for another, say 10. Is that okay? You don't have any pressing engagement, you can always, I'll put this up. Okay, let's go with it then. Because this is what I was talking about when I said that you had a quadratic equation for conservation of energy going with a linear equation for conservation of momentum. And so here are the two solutions. Okay, now you start messing around with the energy, you either make the ellipse bigger or you make it smaller, right? And so you see, right here, the ellipse is bigger than what the vectors are everywhere. It only touches there, and then from there on, the line goes outside of the ellipse. But here's where it's inside the ellipse. Okay? All right, let's take a look at a little bit of the geometry. Okay? Momentum conservation axiom plus the t-symmetry axiom, m equal m transpose implied, gives kinetic energy conservation theorem. This is just stating it as simply as I can. So I've got the ratio there. Now what's so neat about this is this ellipse. This is the equation for the ellipse, but let's turn it into an x squared over a squared plus y squared over b squared, where x squared is VSUV squared. Remember, that's the x-axis for the sports utility vehicle. And then the VW, it's got the y-axis, so we're talking about this velocity squared as being y squared. And then the coefficient here, okay, has to be 1/2 of an a squared. I mean, the a squared has to be 1/2 of that flipped over, so it's 2 times the kinetic energy divided by the mass. This coefficient right here is equal to 1. Standard high school equation, Cartesian equation, right, for an ellipse. So this is your formula for how big is the SUV semi minor axis, or minor radius of the ellipse. A is right there, okay? And then this guy right here, that's this guy right here, okay? We're going to need all this stuff as we do multiple collisions with inside an ellipse like that, okay? So that's key to get those numbers, and the geometry goes with it. And of course, since the radii of the Lagrangian ellipse, we might as well get used to calling this what it is. Lagrange's energy function is always an explicit function of velocity, not momentum. So I tell you that just as though I'm a preacher preaching that, but there are very good reasons for that that are found only when you go into the relativity and see how they really behave at high speeds. So get used to that. And the thing that's interesting here that's geometrically cool and would be hard to prove if you just gave it to somebody as a sort of a math problem, all the lines, prove that all of the lines have the slope SUV over VW. Or if you draw a bunch of those lines, they're all bisected by the slope 1 line. This has to bisect, right? This has to bisect, because every collision that we're going to have inside this ellipse, its momentum line has to be bisected by this 45-degree line, right here, the red line. That's a cool property of an ellipse. The relationship between the ratio of a squared to b squared and a and b. That's really what's going on here, square root ratio. Okay? So I point that out to you, just to, it's food for thought, kind of, things that you would not have even thought of if you didn't do a geometrical approach to all this stuff. But here is something else. Here's a circle that we use to get our solution. Here's something else. There is an ellipse inside there, right here, okay, that represents the energy that you will get if you exhaust all the possible energy that the collision can exhaust. So if they go and crunch, fall together, and then the energy goes away as heat or whatever, vibrations and injuries to various people and animals that are in the vehicles, it stays there at that speed and has a total kinetic energy that's less than what we had for the bigger ellipse. So this is a measure of how much we've lost. Now we have to quantify it. But we have a tensor expression to do that. And that's cool. Okay. Now, if you were to do a 45 drop down, that's Galilean transformation, okay, to the problem that consists of the situation where you're in the frame going 50 miles an hour along a highway in which this collision takes place, and it's totally inelastic. So here you have this hunk of 5 tons of crumpled car, 4 plus of the SUV plus 1 ton of the Volkswagen, going along at 50 miles an hour in your frame now, right? So the kinetic energy of that hunk is 0 for you. And in the book I talk of a cop that's trying to give a ticket to the SUV, right? And the collision occurs, and he was going 50 miles an hour, and now the two are right next to him, so he can just hand the ticket to the SUV driver. But that's the idea. You want to think about how it would be for various observers in this situation. And the cop that hands the ticket is looking at an ellipse that's that big. And this line right here will be tangent to that ellipse. That's cool. Right at the point where they wind up. And I'll ask you to find various ways to make that true at some point, beyond an exam or homework. But it's it's something to think about. There's all these little, it's not a coincidence. It has to be. Okay? But this energy ellipse is 1,000 energy compared to what we started with in the initial energy of 6,000. So big losses here. Okay? Now, we just have a very few minutes to go on and do the algebra that's needed to analyze situations that are in between us. But as usual in physics, opposite extremes are the easy ones to analyze, if you can find them. And in between them, generic real world or real-er world is more difficult, you see. Because if I only do a cohomp, I get an ellipse that's halfway between the COM ellipse and the one we started with. So now I've got another point down here that's different from the ones we were working with. So what in the heck is that point? I'm going to ask you about that later on. But not now. Let's go ahead real quickly and just do the numerical details. Now this is just going through some stuff that's in the text. You should read this to make sure that you're good at it, and I'm giving you a problem that lets you go ahead and work it out, put the numbers in for another situation, just to get you up to speed on the way we think about this thing. So this is, remember, P total is sum of momentum initially, sum of momentum finally, and it's got to be equal to M total times VCOM. And now I'm going to still write the inertial things as though they needed to have a matrix that was full, like that. But we'll keep our old numbers whenever we do a number crunching. Okay, so VCOM times P total, that's going to be VCOM dot M dot VN. That's a nice relation just right there. I saw that relation, I knew I could do everything I needed to do. Just play with it. Write it out in numbers to make sure your arithmetic is right. And that's the other advantage of this, is that it's very easy to do a complete an equation that shows you where everything is. It's also easier to program. And of course that's what most people do nowadays. Get your mathematic out or something and go ahead and do this. Okay, so you check that this guy here is equal to that guy there, and that they sum up to the total. This is a weird kind of action, velocity, momentum, quantity that we're working with, and we'll work with that later on, but that's the other reason for doing this. And then this total momentum is the same at N, fin, COM, or anywhere in between. Now we demand T symmetry, you see. And the important thing is we stay on that line even if you're wasting energy. Do not get rid of your momentum. So there we are again with that, okay? So this thing becomes equal to this and this and this. And you see we have here a expression involving the N and the fin over 4, which is kind of interesting. But what I've done, you see, is subtract this screwy quantity right here. But that screwy quantity isn't as screwy because it's a symmetric matrix. This guy has to be equal to that guy. They're both equal to 10,500. All right, one more page here for formulas. There's the symmetry relationship. And now we look at this product of velocity and P total. And you see that I'll get an energy conservation result. This is equal to that, is equal to this, okay? And that's the kinetic energy that's elastic. Now the kinetic energy of COM is reduced by 1,000 to 0. It starts low at 1,000, not this huge number that we had for 60 miles an hour plus 10 miles an hour. So this one right here with a VCOM, that's equal to this guy right here plus the asymmetric matrix element, both divided by 4. So that's kind of a neat thing. KE in elastic is 1/2 K elastic plus 1/4 of the weird off-symmetric thing. And as you remember, these have to be equal. These two things. It's 10,500. Okay? So that checks. That is the main result. So the difference is crunch. Now, graphical way to look at this. This is the last figure in chapter 2. Here are a whole bunch of different frames. Earth frame view, okay. Initial VW frame view. The VW is standing still in this frame. this over here is sort of halfway in between frame. Nobody's standing still at any point during that collision, or, no, I take that back. I'd have to look at it. Actually, there it is. That's the center momentum frame, COM frame. So they are standing still, both of them, at the middle of the collision, and then they pop out again. This is the final FWV frame. This is a frame in which the SUV is standing still at the end, as you can see from here. Okay. Now, look at this one is as it says here, this one is using a Bush, George W. Bush SUV. Does anybody know the history of that? People do not realize what a destructive administration it was. He made a law, well, he was told to make a law by the rich guys, that if you bought a car that was 6 tons, you could deduct the entire price of that car, which would be $100,000 or more in most of these cases, from your income tax. Just, it's your free. Take that money and go. Okay? But it had to be 6 tons. The idea was, first, burn up more gasoline, because then the oil guys would get richer. The second part was that the automakers would get richer too, because they'd, be putting more metal out on the street. But they had to run and start putting lead and other things into the frame, because up to that point, the idea was to make cars lighter, so they're more efficient. So to make a car that was already only about 4 tons, 6 tons, you had to put 2 tons of crap in it to get it up to 6 tons. They've satisfied the law, and they did. So these are all collisions with a 6-ton George W. Bush SUV, which is more extreme. I thought you'd be amused by it. You should be crying, because what a waste. But anyway, you see we come down here in steps as we go through the various frames. Okay, and I'm just imagining 6 kilograms and 1 kilogram instead of the awful story that actually happened. So with that sour note, I will end chapter 1 and 2, and we'll take on some more fun stuff in the next thing that involves 3 and 4 and 5. Okay, and any questions? We're certainly open for that.
I'll just read the chapters and write a mail to you if...
Yeah, while you're reading, make notes. Also typos, I'm trying to just do a clean sweep of typos on this time through. And parts that aren't clear. It's all fluid, it's all on the internet, it can be changed like that. We don't have to go through some blood-sucking publisher to make a new change. We do it for 0 instead of hundreds of thousands of dollars.
So on Thursday we'll meet at 3:30, right?
And Thursday we'll meet at 3:30, which will be the usual time.
We'll see you on Thursday.
Okay.